Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to 18th lecture of VLSI Interconnects course. Today we will be doing RLC interconnect simulations. Over the last few lectures we have seen that the voltage propagates with a wave nature in an RLC interconnect. We have done detailed theoretical analysis and discussed many analytical methods of modeling these RLC interconnects. We have seen Elmore equivalent models, equivalent circuits, ABCD parameter based methods. In this lecture, we will be discussing the circuit simulation of RLC interconnect. So, we will be simulating the interconnect with lumped RLC elements, but we will try to emulate the distributed nature of your interconnect. So, here we will see that can we observe a wave like phenomena with a distributed RLC interconnect model when we are simulating it in a circuit. So, here is a worksheet for this this simulation. So, some parameters are given to you, an RLC interconnect is given to you. It has resistance per unit length, inductance per unit length and capacitance per unit length. To keep things simple, we have ignored the driver resistance and the load capacitance, but after going through this this lecture you should be very easily able to incorporate those into your simulations. So, it is given to you that the length of your interconnect is 1000 micrometers, resistance per unit length is 0.2 ohm per micrometer, inductance is 0.25 picohenry per micrometer, capacitance per unit length is 0.5 femtofarad per micrometer. Again, as in the case of a RC interconnect, what we will do is that we will give a clock input to this Vi, and we will see what happens to V out of t under different models. So, first we will start with a lumped RLC model, that is the crudest model. The entire resistance and inductance and capacitance is represented by a single lumped element, single lumped resistance, inductance and capacitance. But we will see that do we see an overshoot in the output voltage. So, does that our two pole model for lumped RLC interconnect, does this concur with what we are looking at in this simulation. Then we will simulate this interconnect by dividing it into 5 segments, 5 small sections. Then we will extend it to 10 segments, and then so this will be with R, L and C, but then we also want to investigate the wave phenomena. So, we will minimize or remove the resistance part and only L and C will be there. So, we would expect a purely wave type of characteristics in a distributed LC interconnect. So, we will see that what can we infer from when the resistance goes to 0, and we will compare it with when there is an RLC present. Then we will end this this lecture by simulation of pi equivalent and pi 2 equivalent models. So, this will be very simple once we have done these things. So, let us get started with the first part. So, in the first part what we have to do is we have to simulate the output considering a single lumped RLC model. So, what you have is you have a resistance, an inductance and a capacitance. So, R interconnect, L interconnect and C interconnect. This is your V out of t and V in of t is given here. So, based on these parameters we can find what is my R interconnect, that is R into L. So, I can get this as 20 ohms. My C interconnect is C into L, and if I multiply this here with, this is femtofarad and 1000 micrometer. So, this is in units of micrometer. So, this will be simply 0.5 picofarad, and my L interconnect, which is equal to L into L. So, if I multiply that here, I will be getting a value of, I think, 250 pico Henry. So, I will just substitute them here. I will be simulating this in LT-SPICE. It is the same software which we had used in the previous lecture on simulation of RC. So, I have already made a circuit with these values which we have just now computed. So, if I just run the simulation, this is my input and this is my output, and I can see that for these values I can see there is an overshoot present. So, I can zoom in, maybe I can see that there is a overshoot present here. Now, as per our previous analysis on two-pole model, if I reduce my inductance, I should not be getting the overshoot. So, our argument was that overshoot is because of the presence of inductance. So, let me reduce the inductance. Let me reduce it to say 50 pico Henry. So, if I have reduced to 50 pico Henry, and if then I simulate it, I can see that the overshoot goes away. So, this overshoot increases as I increase my inductance. So, if I make it say 300 and then I simulate it, I should be getting even bigger overshoot here, right. So, this simulation is very simple and straightforward. Now, what is interesting is the additional parts. So, now let us simulate this interconnect by dividing it in 5 segments of equal length. So, what we will be doing is, now I have, instead of one segment, I have 5 segments. Right, and let me call this say R1, L1, C1, R1, L1, C1, L1, C1, and there are 5 segments. So, 5 segments or sections, right. So, the resistance of each one is R, this is R interconnect divided by 5, L1 is L interconnect divided by 5, and C1 is C interconnect divided by 5. So, if I use those values, so earlier this was like 20. So, yeah, so now I would have 4 ohm, then this would be my 0.1 picofarad, and this should be my 50 pico Henry. Right. So, now let us make a circuit out of this. I have already made the circuit. Let me just open that. So, we need to compare this with a lumped model. So, there is a lumped model, I have kept it, and I have these 5 segments. So, let me run this. If I run this, this is my input, this was my output for lumped case, and this is my output for a distributed RLC. So, here now you can see that just like the case of RC interconnect, my lumped model was overestimating my delay, but as the delay is reduced, my overshoot is also now more. So, this is with 5 elements, and I can see that there is a significant overshoot here. In addition to that, I can see certain region where my output voltage remains, region of time where my output voltage remains 0. So, I can see that I can see that for some value of time, my pulse, it takes some time for my pulse to reach the output, right. So, it appears that if I am having a distributed element, I am getting something like type of time of flight. But to validate that, let us increase the number of segments from 5 to 10. So, let us come to the part C, where we want to simulate the interconnect by dividing it into 10 sections. So, here I will be using 10 sections, but if your processor and your simulator allows it, you can test it by breaking it into even more, like 20 segments also, right. And then we will compare we will see how this reflects in the time of flight also. So, here now your R2, so let me still call it R1. So, my R1 now is R interconnect divided by 10, my L1 is R interconnect by 10, and my C1 is C interconnect divided by 10 again. So, my R interconnect would then be say 2 ohms, no sorry, not R interconnect, R1 would be 2 ohms, L1 would be 25 picohenry, and my C1 will be I think 0.05 picofarad. So, we can make it, you can maybe pause the video and make it and then test it on your own. I have already made the circuit, so let me open it up and show it to you. So, here I have all the 3 cases. So, one is the first one is the lumped, V lump, then there is this 5 segment and one with 10 segments. So, here now let me do the simulation. So, here this is my input, this is my lumped output, this is my output with 5 segments, and this is my output with 10 segments. So, if I can see here that now with 5 segment and 10 segments my results are more or less converged. Here however, I can see that I can see something like this time of flight. So, there is some region where there is some zero signal in my output, and then signal starts growing up. So, with 10 segments it seems that I am able to get something like time of flight. But here the effect of resistance and LC is both overlapping. So, RC as well as LC is overlapping in our analysis. So, to investigate the time of flight delay in more detail, let us do one thing, let us reduce the resistance, or let us remove the resistance altogether. So, that brings us to this fourth part, where what you have to do is you have to simulate the distributed model with 10 sections, assuming R going to 0, or you can take R to be much smaller if there is any issue with the simulator. In this LT spice, I have just removed the resistance. So, what I have is just LC circuit, and then we will compare this with the case of RLC circuit, and you can also then go back and check it with the RC interconnect. Right. So, let us look at that. So, again you can pause the video and do the simulation before proceeding. I have already made up the circuit. So, I have this distributed LC model. So, the first one is lumped, we will not be comparing it with the lumped here. The second one is 5 segment RLC, 10 segment RLC, and 10 segment only LC. So, now let me run the simulation and check the output waveform. This is the input, this is the output for 10 segments with R, L and C, and this is the output for 10 segments with L and C. Now this you can see this is interesting, there is this these ripples here. Let me zoom into a region to be more clear, let me maybe magnify. Now in this case here what is our interconnect? Interconnect end is open circuit, right? So the far end is open circuit. From our analysis what we had seen was that my V out in the open circuit case was twice of V plus. So if my input voltage was 1 volt, I would have expected an output voltage of 2 volt, right? So that I can see that. So the maximum output voltage, the maxima in that goes close to 2, but it does not go reach 2 in this simulator. So even though I have not included any resistive or absorbing components, it seems that in the simulator there is some to avoid any numerical inconsistency or singularities in computation, there is some absorbing element introduced somewhere in the source or in the signal generator. So here, because I can see that there is this damping, it takes time, but there is this damping which is there. In a purely LC interconnect, I would not assume there won't be any absorbing element, and even if you give one pulse initially, there would be a ringing going on throughout. But here there is some resistive component included here. Now let us look at this in more detail. So what I have done is I have actually taken this snapshot already and included it here. So this is my case. So let me highlight this. This is my LC, and this blue curve is my RLC. If I zoom into them, so I have again zoomed into this region, and this zoomed in region I am showing here. So here I can see that this is my LC and this is my RLC. Now I would have theoretically assumed that if a pulse comes here, like I had shown in the simulation or say the animation in the previous lecture, that a pulse would come travel here. So so my input would have come traveled like this, and from here it would have gone up, right. So this would have been my ideal case, like an input pulse comes, there is an LC wave propagation delay, and then my pulse would have been here. So I would have expected that there would be a time of flight delay in this. So this would have been my time of flight delay TF, right. But in this case I am not getting directly like this, but what we can see is we can check what would be this delay and does it coincide with the theoretical value which we can compute, right. So let us check that. Let us check whether this time of flight delay is actually corresponding to the theoretical value of time of flight that we would be getting. So what is my phase velocity? My phase velocity is 1 by root over LC, and my time of flight would be the length of the interconnect divided by the phase velocity. So if I look at this, this should give me a value, and then this value should somehow coincide with somewhere here, right. So let's look into that. So I have already done the computations, so you can check the calculations. So here your inductance is in the units of Henry. I have taken this micro in here. So Henry per micrometer. This is in the units of Farad per micrometer, inductance per unit length, capacitance per unit length. From here you can get Vp is equal to 1 by root over LC, and since these are in units of per unit, in units of micrometer, the Vp you will get is in the units of micrometer per second, and so if I solve it, finally I get this is in the units of micrometer per second. Length is in the units of micrometer, so if I get find out Tf, which is L by Vp, it comes out in the units of seconds. If I convert it into units of picoseconds, I get something like 11.18 picoseconds. So let us go to the simulator and see whether this makes sense. So let me introduce a marker here. I hope the values in this thing are readable. If not, I will be also saying them verbally. So if I bring it here, I can see that this reading here is 11.246 here. So this value is reasonably close, right? Considering the accuracy of pointer where I am placing and all, this is like reasonably close, 11.24 picoseconds. Now, however, we need to check one more thing. So the important thing about this time of flight delay is that your Tf is L by L into root over LC. So this is different from your RC delay. So your RC delay, right? So your RC delay scales with proportional of L square, right? So your Td was RC L square by 2, whereas your this delay is proportional to L. So your Tf is proportional to L. So if I increase my length, so if I make a if I make my interconnect length twice, so earlier I had L, but now I just extend it to 2L. So now I have 2L. In that case, my time of flight, if this lag is indeed because of the time of flight phenomena, then this should also double. So my time of flight should, my Tf prime should be twice of my Tf. So let's check that. So for that, what I will do is that I will extend the length of this interconnect. So I had 10 segments. I will add another 10 segments here, while keeping the values of each element the same. So I am not breaking the interconnect into 20 segments now. What I have is I had, yeah, so let me close this. I have already made the circuit. So I had this 10 segments. The values I have kept for R, L and C of each element to be the same, but I have included 10 more segments. So this one is twice the length. So this is 2L, this is L. Now let us simulate it and then compare. So this was my input, and this is my output for 2 elements. 10 elements, 10 segments. This is for 20 segments, but corresponding to 2L. So here we can see the output comes out to be like this. In the previous lecture, towards the end, when I was showing the animation, I had made a statement that the periodicity here would depend on the length of your interconnect, because that's how you are getting these ripples. Wave comes, it hits the far end, then it gets reflected back, then it comes back, then again it comes here. So there is back and forth movement, and here you can see that since the period is now the length is more, the period is also more, period of these ripples is also more. Now let us zoom into this region to see and measure the delay. So here the first one was around 11, right now I am seeing 11.6. Let me fine tune it. So this is like 11.2423, 11.42, and then I add say another cursor here, and then I bring it close to this and this here. So here I can see that my difference right now with these markers which I have placed, the difference comes out to be 11.03 picoseconds. So these are not very accurately placed, these are like computed numerically, so it moves in steps only. So if I bring it here, it shows me 11.23. So we would have expected that this was TF and then this was another TF. So your total gap would have been 2 TF. So that we have validated here that this is actually, this is TF and this is 2TF. Right. So with this circuit, RC circuit, lump circuit simulation also, if you have enough number of elements, you can simulate the wave type of phenomena here as well. Right. So so the final simulation that we will take up is the simulation of interconnect with pi equivalent model and pi 2 equivalent model. Then we will compare this with the case of a distributed RLC interconnect with say 10 or 5 elements. So here we will evaluate this pi model on 2 parameters. One is like the overall delay. So if only the overall delay is our concern, are these good enough? And if we are also concerned with the time of flight delay, which essentially comes because of the distributed nature when you have large number of RC, then is this lumped pi equivalent model good enough? So your lumped equivalent model will be, so this will be your pi 1 model and this will be your pi 2 model. And then you can compute these values and then make the circuit. Let me go ahead and open the circuit that I have. So if I then, so I have already made this circuit. This is with 5 elements, I am comparing it with 5 elements, then there is a pi 1 and then pi 2 model. So this is my input, this is my pi, this is my lump pi 1 and this is my pi 2. And then if I look at this plot, I can see that if I zoom in, I can see that I mean this red one is my pi 1 and this final one is my pi 2, right. This my sky color is my pi 2, this dark blue is my 5 segment interconnect, distributed interconnect. So here we can see if we are interested in overall delay, I mean how long it takes to reach 1 volts, even the pi 1 model is good enough estimation. But if we want to see what would be the actual waveform of your output voltage, in that case we require more distributed nature. So with say pi 2 elements, we are able to not exactly but very closely replicate this region as well, right. So here you can see this dark blue is the distributed model, right. So that's all for the simulation part. Let me summarize. So in this module we have seen the inductance in interconnects, the origin of we had discussed in detail what is the origin of this inductive effects in interconnects. We saw the distributed model and we saw that because of this presence of inductance, a wave phenomena is introduced in the way signal propagates, and then we require transmission line equations to model it. We also saw that when and why inductive effects become important. So we saw the conditions where we can ignore the inductive effects completely and our RC interconnect analysis is good enough. Then we saw some analytical methods based on two-pole approximation, which included Elmore equivalent and ABCD parameter based extraction of a two-pole transfer function. And in this lecture, we saw the SPICE simulation of RLC interconnects. So this is the last lecture of this module. In the next lecture onwards, we will be starting with the third module of this course, which is on the additional effects in interconnects. And the first additional effect that we will take up for discussion is the skin effect. That's all for today. We will meet in the next lecture. Good day.